Hello, my name is Samantha Botros, and my project is the Spatiotemporal analysis of dengue incidence in Colombia associated with movement and climate patterns. Dengue is a serious viral disease with 4 different serotypes that are transmitted by the Aedes aegypti and Aedes albopictus mosquitoes. It is considered to be the most prevalent arthropod-borne viral disease known to man. The annual number of infections exceeds 400 million people worldwide and causes over 20,000 deaths. The disease is especially prevalent in tropical areas with poor living conditions. Over half of all dengue cases are asymptomatic, which is problematic with respect to infection rates. However, symptomatic cases occur 4 to 7 days later. This initial phase is known as dengue fever, characterized by an array of nonspecific systematic symptoms as illustrated in the diagram. These symptoms can last anywhere from 3 to 14 days. A severe form of dengue disease is dengue hemorrhagic fever, which presents similar systematic symptoms but also includes hemorrhagic manifestation, increased vascular permeability, and/or thrombocytopenia. If medical attention is not received in a timely manner, this can develop to a fatal condition known as dengue shock syndrome. There is a widespread presence of the Aedes aegypti mosquito in Colombia, so it should be of no surprise that dengue is an endemic disease in this country. The majority of Colombian citizens live in areas of high risk due to the unfavorable environmental and living conditions present throughout the country. This study, published in 2015, showed that nearly half of all dengue cases in Colombia during the years 2000 to 2011 originated from 18 municipalities. There are an array of factors that could cause these municipalities to have higher incidence of dengue, ranging from climate to sociodemographic factors. As you can see here, there are a vast number of factors that contribute to incidence rates of complicated diseases such as dengue. Not only does each factor impact incidence individually, but the interaction between multiple factors plays a key role as well. This study focuses on human migration, population size, and environmental factors, specifically through a spatiotemporal analysis of observed patterns both individually and through multifactorial interactions to determine how said patterns influence incidence rates of dengue in Colombia using data from 2010 to 2015. The collection of data that is analyzed in this study came from 4 different databases. The number of cases of dengue throughout Colombia came from the CVHILA database, which is part of Colombia's National Health Institute. Migration data is from the Registro Único de Víctimas. Climate data is from the Institute of Hydrology, Meteorology, and Environmental Studies. Lastly, consensus data is from DANE and was obtained through Colombia's National Statistics Agency. The majority of the data processing and analysis was done in MATLAB. However, R and Google Earth Engine were briefly used for some of the data processing as well. With respect to the spatial aspect of the study, a patch system is used. Depending on the spatial resolution of interest, the area in each patch will vary. In this case, each municipality represents a patch. Therefore, there are a total of 1,222 patches in Colombia. However, not all 1,222 patches are analyzed in this study. The first filter is to use only municipalities with disease data registered in CVHILA. Then, according to DANE, the population of the municipality is greater than 30,000 in the year 2018. Lastly, the municipality has a minimum elevation of 2,500 meters. After this, we are left with a subgroup of 235 municipalities of interest. As mentioned in the objective, the study consists in analyzing how these 3 factors, climate, movement, and sociodemographics, influence dengue incidence in Colombia. Not only how each factor directly affects incidence, but how the interaction between different factors uniquely affects incidence as well. In this case, incidence represents the number of cases of dengue per month for every 100,000 individuals. With respect to sociodemographics, we focus on population size, which is divided into 5 subgroups. We then make annual heat maps of incidence from 2010 to 2015 for each population subgroup. For now, the only environmental factor analyzed is precipitation. Firstly, we make heat maps of the average monthly rainfall for all the municipios of interest, and then a correlation between average monthly rainfall and incidence. The last factor analyzed is movement. As you can see from this graph, there are different levels of temporal and spatial scales associated with movement. In this case, the study uses only displacement data. On the temporal level, this constitutes as migration since it's assumed to be a permanent move, while on the spatial scale, analysis is conducted on both the country and regional magnitudes. The movement data is organized as the number of ingoing and outgoing cases per municipality per month. An important aspect of this part of the study is that given Colombia's turbulent political history, the grand majority of this displacement is due to armed conflict. The monthly analysis first consists of annual heat maps on monthly movement alone that is divided into different population subgroups. Then a lab correlation is done between imported cases and incidence to determine if there's a delay between entry rates and its effect on dengue incidence. The figure on the left shows the average incidence for all 235 municipalities between the years 2010 and 2015. There is a peak in incidence between the months of February and July. However, municipalities that did not have this prevalent peak incidences during this mid-year window appeared to have a gradual increase in incidence throughout the year. The figure on the right shows the incidence in 2015 for municipalities with a population between 30,000 and 50,000 inhabitants. This population bracket had the highest incidence rates. Additionally, there is a similar peak observed between February and January independent of population size. However, in this year, there also happened to be a much higher incidence rate in December. The figure on the left illustrates the monthly average rainfall for all 235 municipalities between the years 2010 to 2015. There are two peak rain seasons, April to May and October to November. Also, January to February appear to be the driest months of the year. The figure on the right is the correlation between precipitation and incidence for all 235 municipalities from 2010 to 2015. The general trend observed is an increased correlation in March or April, June, and October or November. This relates closely to the rainy season findings. Also note how many of the incidence rates are relatively low in the dry months in the beginning of the year and drastically spikes between March and April. The following figures are the outgoing and incoming monthly movement data respectively for municipalities with a population size between 50,000 and 75,000. The movement matrix shows that Tame, Vicente de Caguán, Puerto Asís, Valle del Guames, Osis, y San José del Guaviare are the municipalities with highest outgoing movement, and Vicente del Caguán, Puerto Asís, Valle del Guames, and San José del Guaviare were the municipalities with highest incoming movement. This figure shows the top 3 municipalities with highest incoming movement rates, outgoing movement rates, and incidence rates respectively in 2015. There's an evident relationship between municipalities with high incoming movement rates and high incidence values. The figure on the left is a monthly lag correlation up to 6 months between the incoming index and incidence rate. There is no pattern on the number of months prior affecting incidence. However, there is a pattern indicating movement months associated with higher correlation to increased incidence. The figure on the right shows that March, September, and December are the months of movement associated with higher influence on incidence. With respect to temporal incidence patterns, there's a 6-month window where dengue incidence tends to be highest. Peak of incidence of dengue occurs between February and July in all municipalities, regardless of population size. Municipalities that do not present peaks in this mid-year window tend to gradually increase incidence throughout the year, with peak incidence values in November and December. These temporal patterns are not influenced by the population size of the municipalities. However, the incidence of dengue is highest and most prevalent in municipalities with a population size between 30,000 and 50,000 inhabitants. Across all 235 municipalities, there are 2-month intervals with high rainfall values, April to May and October to November. On the contrary, January and February are the driest months of the year. The 4 rainy season months had the highest correlation values to dengue incidence. With respect to the temporal incidence patterns, both rainy seasons correspond to months with peak incidence values. Therefore, the amount of monthly rainfall is positively correlated to the incidence of dengue. This could be due to the lack of adequate sewage systems. A buildup of water in the streets would attract the disease-carrying arthropods. Municipalities with higher incoming migration rates tend to have higher incidence rates. There is no statistical difference of this pattern based on population size. Movement during March, September, and December were correlated to incidence rates. March and December tend to be peak incidence months, thus there's no lag associated. However, September tends to be one of the lowest incidence rates, meaning that those who migrated during this time were likely non-symptomatic and infected at least 2 months prior during the 6-month mid-year peak. The end goal is to create a statistical model to predict monthly dengue incidence and monthly dengue intensity using spatiotemporal movement, climate, urban morphology, and sociodemographic patterns. Before this analysis can be completed, incorporation of urban morphology and socioeconomics is necessary. Furthermore, the same analysis needs to be done with dengue intensity. And lastly, other environmental factors such as temperature could be incorporated. Lastly, further spatiotemporal analysis of movement could be done to understand migration patterns and its correlation to armed conflict in Colombia. I'd like to thank Pallavi, a PhD candidate at Columbia University, for her guidance in the development of this project, as well as Mauricio Santos, a postdoctorate at Los Andes University. Thank you for taking the time to listen to this presentation. If you have any questions, comments, or concerns, feel free to send an email to the address on the screen.